So, can you hear me in the back? Awesome. Let's start. So, my name is Bilan, and today we're going to talk about this new paradigm in NLP called self-attention. So, actually, like a couple of months ago, I saw this blog post by Eugenio Culurcello, and he writes, drop your RNNs, drop the LSTM, don't use those anymore. You don't need that. You only need attention. Attention is all you need, right? And when I read this, I was like, what? Like, we did this for 3 or 5 years, and we were so successful, and now we're just supposed to throw it away? So in this talk, I'm going to answer this question, like, can we actually skip the whole part and just use attention? So let's take a quick step back. I'm currently studying computational linguistics at the LMU. I'm also studying technology management at the same time. I'm doing a lot of research, mainly in relation extraction, author profiling, author obfuscation, and stuff like that. If you're interested in any of those, come up to me later. And I also work as a part-time data engineer at TrustU. So just very quickly, at TrustU, we do automated summarization. We collect a lot of reviews from the internet, and then for each hotel in the world, based on the reviews they get, we output like one-sentence summary, like for 600,000 hotels. Okay, so let's jump right in. First, let's take a look at how the sort of neural NLP has developed. So we all started with RNNs. In an RNN, you get a sequence, a sentence, and then you just go from the first one to the last and encode information. In the end, it sort of outputs an encoder that is like a sentence embedding. But their RNNs didn't really work that well. Well, they are a bit more complex than that, but there was a problem of like the gradients not propagating properly. You're losing a lot of information. So that's why people came up with long short-term memory and gated recurrent units. So basically, it's an improvement over RNN, which just adds up more logic that helps the model decide whether the input is important or not, and should I propagate it to the next step. So they use sort of something called gating mechanisms, and this is the whole logic that's in there. Well, people also use CNNs for NLP. Well, when I first started, this was really weird for me. Like, how can you use a CNN for NLP? Well, the best way to think about this is in the image, you have pixels, and then you have sort of height and width. You actually, and then you do like max pooling and stuff like that, or that. Well, actually, you have the same thing in sentences, because your height is like the number of words in the sentence, and the width is the dimensionality of the embedding of word-to-vec embedding, for example. So that's how you can use CNNs. Right, and LSTMs are often used in an architecture that we call encoder-decoder, or sequence-to-sequence. Especially this is used in neural machine translation, where you like input a sentence in German, and then it will output a sentence in English. Right, and this looks kind of like this. So the red part is the encoder. You can use LSTM, GRU, whatever you want, and somehow you encode the sentence and create a vector Z that is sort of like a sentence embedding. And then you give the sentence embedding to your decoder model, which can also be an LSTM, but doesn't have to, and then it will sort of translate it. So this is a really nice example where it's translating an idiom from German, echt dicke Kiste. It's actually translated correctly in English and says it's awesome sauce. Right, but, so LSTMs were kind of created to deal with this vanishing gradient problem, so the information not propagating, and sort of LSTMs were supposed to fix this, but this is a sentence. This is like, I don't know, 50 words long. This is from War and Peace by Leo Tolstoy. And like, are we supposed to use an LSTM for that? It's not really going to work. So what's the solution here? We move on to attention mechanisms. You can use attention to improve LSTMs as well as CNNs, either for NLP or for image recognition. So let's first start with understanding images. This is a model from DeepMind, and it sort of hops over the image, but only attends to the most important part. So here it's classifying like house numbers. And you see it doesn't scan the whole image, it only scans the part that has the number in there. Well, actually, it's very similar in NLP. When you read the text, you often skim through it. You don't really read the whole thing all the time, and maybe only some parts of it are important, some are not. So this is a sort of model that uses LSTMs with attention to do summarization of restaurant reviews and beauty salon reviews. And you can see the red part is actually where the model is paying the most attention. So it's saying like, this is a nice place, my favorite restaurant, food is incredible, and so on. So the model is actually selecting the stuff that's important for the summarization. Right? And you can also use this attention in the encoder-decoder model. When you're translating from one language to another, you see the width of those lines actually show you how much attention the word you're going to translate is paying to other words in the sentence. So the bigger it is, the more attention it pays to it. Right? It's a bit more complex than that. There are a lot of formulas. But when you deal with attention, you can either use it for translation, but you can also actually use it for simple document classification. Like you can just create an attention over words to build a sentence embedding, and then over that, you can build sort of document embedding based on the sentences, and you will only attend to the sentences that actually should like contribute to your classification. So I'm not going to go over the formulas, but when you deal with attentions, most of the time they look like this. So the first part, the U, is the context vector, and there are many ways how you can do this. So there's no standard way for attention. That is why, like in PyTorch, TensorFlow, there is no layer called attention. You just have LSTMs and RNNs because there are so many of them. But the next part is almost always the same. You just do like a softmax operation to get the probability, and then use those probabilities to improve your LSTM or whatever you're using. Right. So actually, this helps a lot. On the left side, you see in neural machine translation, we use a blue score to say how accurate the translation is. And if the sentence has more words, has more than 40 words, then it sort of goes down. But on the right side, where you have attention, that sort of stays stable, even if sentences are really long, like 60 words or even more. So that works quite well. Well, actually, it also helps you to see what the model is learning, what's it attending to. So you can look at those weights, what words are contributing to other ones. So you can look at individual words. Let's say this from French to English, this word is translated, and it looks to economic area or whatnot, and then you do another one. And sort of you can also debug your model this way, but also sort of visualize it. Right, so we saw we can use attention to improve LSTMs, but it's also possible to skip the whole LSTM CNN part and use attention. So this was first done by Google Brain. They published a paper in July 2017, so a year ago, where they don't have any convolution, no recurrence, it's just layers of attention. And sort of very high-level overview, it just takes one word and then compares it to all the other words and tries to get the similarity. And it's like a set operation. It doesn't care where the word is, so it just compares everything to everything. And then based on that, it encodes this information, passes it to the decoder. And then decoder can also attend to like separate words. Right, so the model is actually quite complicated, but we'll try to figure it out, at least on a more higher level. So on the left side, you have the encoder, and the right is the decoder. Basically, there are only few like specific layers in there that are then just repeated or used in like different constellations. So we start with our sentence, which is encoded in Word2Vec or whatever. And I told you it's a set operation, right? So it's like the model doesn't know where the words are positioned. So the authors actually had this very interesting idea of, instead of passing like indices of words where the words are situated in the sentence, they use wavelength functions to generate a wave that will then show where the word is in the sentence. I'm going to show you more example on that, just keep that in mind. After that, you have this block, the whole encoder. And in the encoder, first, you have multi-head attention, which is like actually the soul of the whole architecture. This is the self-attention itself. So we're going to look into that in more detail, but let's talk on the, let's see what it is on the higher level. You have also residual connections. You probably know that from imaging algorithms where you do something with the input, you don't want to lose too much information. So in the beginning, you make a copy of it, and then add that copy to your output later, so that you sort of still keep that information. And then in the end, after this whole multi-head attention, they have a sort of feed-forward network that is trying to figure out what the attention was outputting. So it's very simple, like using activation function weights and biases. And in the end, you have to somehow, to normalize the output. So you probably heard about batch normalization or layer normalization. So the authors here using layer normalization for neural machine translation, for them it works quite well. Right, and then the decoder is sort of almost the same, it's just structured a bit differently. An important part, now you can also have multiple layers. So the encoder can be 6 layers. It's the same that you would do with LSTM. So you can also have multiple layers of LSTM. And then the multi-head attention, it's also copied, but you're going to look into that very soon. So I told you about the positional encodings in the form of a wavelength. So basically the authors say, hey, I'm going to have this function where I give the index position of a word, and then I do some math magic with some constants, and in the end I'm going to get a wavelength. So it can easily be visualized like this, but this is another visualization of that. So you can see there, this is word number index 0, word 1, 2, 3, and so on. And then for each position in a sentence, it's kind of generating those things. And actually the authors say, oh, that doesn't really make that much difference. What they do here, you can just use typical positional embeddings, but there's one difference. When you during your training, you see only sentences that are up to length 60 words. So when you're predicting and the sentences are longer than the 60 words, and you're just using learned positional embeddings, they're not going to work, because your model has never actually seen word at position 61 or 62, because that wasn't present in the training model. So, but here, if you use this function, you just say, hey, here's position 62, generate me this wavelength. So this can actually help the model to work with even longer sentences. Right, but this is very absolute, so it's just encoding it for one position. Then there was a follow-up research by the same authors. Basically, they say, hey, we can have relative positional embedding. So let's look at the context. Let's see, maybe they have a window, 2 words before the word I'm looking at, 2 words after that word, and then I'll try to also get the context. How are the embeddings looking for that word? So actually at the LMU in my university, we had this idea as well, even before the paper was published. But we have a sort of different implementation. We also use relative embeddings, but instead of having a window that sort of moves, we use something called positional binning. So let's say next word is very important to me. The word after that is also important, but words like 3, 4, 5, they're not so important. So let's bin them up in one class, sort of, and they all get the same weights. And then if they are even longer, far away, then make the bin even bigger. So yeah, the attention, the multi-head attention, the sort of soul of the architecture, is actually very simple. I'm going to explain everything. So it uses this idea that you can use queries to extract some values. And the query is your word encoding. and then you somehow create those two matrices, keys that you can do similarity with, and then values. So I told you in the beginning, I take one word, and then just try to look how similar are other words in the sentence to the word I'm looking at now. And in order to do this efficiently and fast, you have to have these separate matrices to do that. So let's go over an example. Say I have the sentence, right? It's from word 1 until word n. And my words are encoded with word2vec or whatever. So in the original model, they have 512 dimensions. And then you do the positional stuff that we talked about. You just add them up. So you sort of also add this information where the words are situated in the sentence. And then let's say, okay, let's look at one word, word at position x2. I want to see how similar are other words to that one. So I use something called compatibility function. And I say at position 2, look at position 1, look at position 3 and 4 and so on, and let's find out how similar they are. And you can do this by using this trick with like key matrices, and in the end extract the similar words using the value matrices. So if I do this for position 2 and 1, I get some sort of similarity. Maybe this word is a bit similar. When I compare it to itself, of course it's the most similar because the word in the sentence is most similar to itself. And then let's say, for example, the word 3 is even more similar to that than the word 1. Word 4 is even more, so that means, hey, I need to pay attention to this word 4 when I'm looking at word 2, because somehow it's similar. And you do this for the whole sentence, and now you have to somehow use it. So you can run a softmax operation. Basically, softmax will give you a probability distribution over all of those similarities that you have just computed. And now you can use this probability to create this top-level z-vector. It's like we saw in the encoder, LSTM creates those z-vectors that are sort of like a sentence embedding. And here, you're basically doing the same thing, but you're not using recurrence or anything else. You're just using this attention mechanism with similarity, right? And then you do this trick where you multiply this similarity probability with this other matrix of values, and then this is how your encoding in the end looks like, right? And you do this a couple of times. Basically, you multiply your heads, and you have different heads. And actually, they are in the beginning the same, but all of them have different weights. So they learn something else. Each of them learns something else. So the head on the left, sort of here you can see it looks very closely to the words next to it. And the word on the head on the right, it kind of attends to words that are further away, right? So it's sort of learning something from there. And then there are also other examples where somehow figures out, like coreference, what are words referring to. Like if I have the animal crossed the street because it was too tired or didn't cross the street, and then it was too tired, the head can actually figure out what it is referring to. Is it referring to animal or to the street? So yeah. And then when you try to re-implement this model yourself, you're just going to fail because there are so many details, it's just ridiculous. A lot of constants, lots of stuff. One example is you can't really train it the usual way. You have to do learning rate warm-up, which means you start with a learning rate 0, and then you increase it gradually over like 4,000 epochs, and after epoch 4,000, you sort of decay it. And for some reason, this works better when you're doing like neural machine translation. And then this model is training for like 300,000 epochs. But that's probably because it's Google, right? They have tons of data, so they need more time. Right, so don't do this from scratch. There is an official library from Google created in TensorFlow. There are also other ones in MXNet, in PyTorch, and you can also find like really nice blogs that try to go over the code and explain how it is sort of implemented. Right, so we saw self-attention can be used for neural machine translation, but there are actually other applications. And again, Google Brain, they used it for something else. They tried to quickly summarize text, like based on Wikipedia articles, and then they can also generate new Wikipedia articles, like fake ones. And they have an example where the model generates a Wikipedia article about a Japanese metal band with like Japanese names and cities and whatever, and it looks so real, but it's actually totally fake. The model has learned to sort of create those texts itself. Then we, at our university, a team of researchers used it for like relation argument extraction. So we're going to come back to that in a bit. Then there's some research by Berkeley University. They use self-attention encoder to improve constituency parsing, and they are actually beating the state of the art, which I think was previously like LSTM based. And then right now there's a lot of research going on into self-attention by OpenAI. They saying, hey, we trained this like task-agnostic language model that can do lots of stuff, like question answering, textual containment, reasoning, and it's all based on sort of self-attention. There is a preprint. It's not published. They're still working on it, but it's really cool. And you can see the dates. It's like everything is like super new. This all happened in 2018. So this area of research is like really new, but also very exciting. So just quick note, Google is not the only one doing this. There is also another self-attention model, which is called DSAN, like directional self-attention. I'm not going to talk about that because that would need like another presentation. But just so you know, there are like other options to do this. Okay, so now I want to introduce our research from the LMU. We actually used self-attention encoder to do a relation classification. And this is done together with Benjamin Roth. He's a professor of computational linguistics at LMU. And we basically worked on this for the last half a year or something. So what is a relation extraction? Let's first have a couple of examples. So in relation extraction, you try to extract some information from sentences. You have two entities in the sentence, and then you try to find, hey, what is the relation between those entities? For example, relation person, employee of. You will figure out, hey, does this person X work for company Y or whatever? And I have an example for that. For example, sentence go, AIG intends to sell shares in American Life Insurance Co., blah, 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 said Fumiyoshi Sado, a Tokyo-based spokesman for AIG. So you have two entities. One is Fumiyoshi Sato, the other one is AIG. And then you tell, hey, look into this, and what is the relation here? What is the relation in this sentence between Fumiyoshi Sato and AIG? And then the model looks at the sentence, and based on what the sentence has, like all the other context words, it decides what relation it is. So yeah, and why you need relation extraction? Well, basically you use it in many ways. First, you can create like knowledge databases, ontologies. You can use it in question answering, summarization. This technique is even used in biology to like find protein interactions, and like there are many use cases for this. So before we had like neural NLP, we had this feature-based approach. It did some parsing and stuff, and it had rules. And one of the rules is, hey, look if there exists some dependency tree that is not longer than 2 words and whatnot. So this was like state of the art until 2015. And then came along some neural models. We used CNNs, we used LSTMs, and they improved a lot the state of the art. And the sort of the final state of the art, and up until now, was from Stanford NLP. They had this idea to use an LSTM with attention, but they improve attention. They call it position-aware attention. So actually, I told you in relation extraction, you have two entities. And what they do is they encode separate positional embeddings for those entities. So they say, oh, my first entity is at position 5, so let's create like an embedding for that. and my another entity is somewhere in the end of the sentence, so I have a different positional embedding for that. Right, and then they use LSTM, and I told you like you're going to see this formula a lot, because that's basically how you do attention, and as I've told you, they sort of have their own idea of how to create this context vector, and the rest is the same. And also, they didn't just create the model, they also created a really nice data set. It's quite huge, it's 120,000 examples, and it actually has 42 relation classes, which is a lot. And it's relation classes like for persons and for organizations. One thing is, this data set is very complex because 80% of it is like examples where there is no relation. Let's say you have a sentence, Mike is working as a teacher. There is a relation that Mark is a teacher, but if you have a sentence, Mike is not a teacher, then there is no relation, like it's a negation. So the model has to also figure this out. Or if you have a sentence, Jane likes to travel around the US, is there a relation between Jane and the US? Maybe there is some, but it's not important to our database. Like we're not building facts about where Jane likes to travel to. So there is no relation in our model. And they get like 65.1 F-score, which is quite high considering you have 42 classes. And the sentences are really long. Like the average sentence length is 40 words, and the longest one is like 96, which is quite a lot. So yeah, and then we implement a new model. We use self-attention, plus we use this part of position-aware attention. So we, in the end, combine them. First, let's look at self-attention encoder. This is what we had before. This is what I tried to explain to you. And then this is our modification of that. So we change a lot of stuff. I told you we have our own implementation of like relative embeddings. And then we don't have two residual connections. We only have one because we saw this works much better for the task of relation extraction. Then we also even changed like activation functions. We found out that ReLU is not working so well here. Random ReLU is much better. Also, layer normalization doesn't work. We tried like different techniques and saw, okay, batch normalization is working much better. Then we changed a lot of stuff. Maybe the most important one is that we don't have to train for like 300,000 epochs. The model actually converges in just 60. Maybe it's just because less data, maybe it's just the task, but it's just taken like 1 hour to get really good results. So how do we combine that? I told you, hey, this part is sort of generated by an LSTM. So let's just take that away and plug in our output of the self-attention encoder. So we give this Q vector or Z vector, and then we also change this other thing. They say they also want like a final output of the LSTM, which is like the final sentence encoding. And we say, okay, we can also provide that. We just do like a max pooling layer of our self-encoder output. And hey, we are completely replacing LSTMs in this case. So this model is attention only. It has self-attention, and then on top, it's using position-aware attention created by Stanford. So yeah, what are the results? If we compare that, we are getting better results. Well, not that much better, just 1.5% in general if you're using one model, but still better. Like we are the new state of the art, basically, at least based on that data set. What also Stanford NLP did is they also had an ensembling model, so they tried 5 models with different random seeds and then did majority voting over that. And we do the same thing, and for some reason the ensembling doesn't really work that well. We are like 0.1% better, which is, not so much, but still a bit better. Right. For this was all done in PyTorch and Python, obviously. So, I've been working on this for the last half a year, and I really like PyTorch. Coming from Theano or TensorFlow, I really like programming in PyTorch. So yeah, I guess that's about it. Get in touch. Unfortunately, our research is not published yet. We are still working on it. but we will probably have a preprint next week or in 2 weeks on arXiv, and I hope in August we'll release the source code so that everyone can use it. Yeah, I get lots of references. Take a look at those. Thank you for your attention. That's not a pun.
Thanks very much, Ivan, for a really nice talk. Are there any questions in the audience? Yeah, over here.
Hi, thank you for the talk. I have a question about memory consumption of the model. As we can see, like for example, in the hierarchical attention models, you basically compare every time with a context vector, and here you store matrices with like similarity from all of the words to all of the words. How extensive it's for memory if you're using if you don't have that much power as Google has.
You do use up more memory, but it's much faster because it's parallelized. So each head from this multi-head attention can be calculated in parallel. You do get, like, you need more memory, but for the example we did with the relation extraction, it was okay. Like, I had a GPU that's 6 gigabyte VRAM, and it still was fine. Like, you don't need a, I don't know, V100 over there.
Okay, thank you.
Sure.
Yeah, thanks very much for the interesting talk. One question on the latest research you did and presented today.
Sure.
How did you come up with the changes you made to the architecture your new model is based on?
So some of it was based on previous research from our university, but the rest was many times trying out things. It's like, deep learning is basically trying out stuff, and maybe it will work. And I had half a year for that. So, in the end, so in the paper we're going to publish, I try to explain everything that we tried, so then you don't have to do it again. So wait for that. There's everything explained. But this actually was a lot of trial and error, but in the end, the results are pretty good. Sure.
Any more questions somewhere? So I have one related question.
Sure.
So do you actually do a proper feature ablation study when you you did a lot of changes? So do you actually explore which part of the change of the architecture is getting you an improvement of how many % on that data set?
Yeah, actually we do. It will be in the paper. So I have a table comparing all the results. And we also try to visualize the models. Like I showed you, you can visualize attention, and you can do the same thing with self-attention. So we go over some sentence examples and try to see, hey, what's changing and what's better. So we actually debugging it sentence by sentence sometimes to figure out, hey, does this actually work or not?
And what was the most important architecture change?
I think the residual connections, like if you only have one, and then batch normalization was huge impact. And actually also using this position attention layer from Stanford helps a lot, because if you only use self-attention encoder, which you can do actually, the results are half of the state of the art. So you actually need this additional attention layer for that.
Okay, thank you. Any other questions? We have plenty of time for one or two. Over there.
I was just wondering why we use cosine and sinusoidal functions for the positions. I didn't get this part too well.
Yeah, I think it was just a gimmick for the paper, to make it look cool. But actually, they actually say in the paper, hey, you can just use typical positional embeddings, and the results are the same, right? But I told you there's one difference, right? If you train a model that only sees short sentences, when you do typical positional embeddings, it can't learn anything about the positions that are like over the ones that you saw. But if you just run this like over cosine and sine function, it will actually give you a wavelength. So you kind of can learn something from that. So that's like the biggest difference I see there.
Wavelength is like, do you do any transformations on these functions later on to get this wavelength?
Yeah, they like dividing by some constants and stuff. And the constants are just, again, I think trial and error from the authors of the paper. They just tried so many things and say, oh, okay, this works, right? Maybe they have some explanation for those, but it's hard to like find. The paper is like really short.
Great talk, thanks.
Thanks.
What do you think? Is attention really all you need? Is it going to replace CNNs and LSTMs?
I think so, especially not just based on our research, but I told you OpenAI is working on this. They have like really, really promising results, and they haven't like fully published yet. So I'm hoping they will bring out something really cool, and then maybe we don't really need to use LSTMs anymore. Yeah.
Thank you very much. More questions or yeah?
No.
I have one more question. How can it deal with the with text of different lengths? For example, I have, I don't know, comments which are like 200 words, and also the others who are like only 5 words length.
Yeah, because the attention, the whole point of attention is that you look like at word 200, but you always have this reference vector with all attention, so you can just look back and see, based on the probability distribution, what are the most similar words to the one I'm looking at. So I can actually, maybe the word one is more similar, right? And this, for example, the difference between German and English is in German you have verbs like in the end of the sentence. So the LSTM wouldn't really work that well, so you need like by LSTM that goes both ways. But here you don't need that because like it's always even distribution and it always knows what to attend to.
Mm-hmm. Okay, thanks.
Sure.
Thank you very much. So let's thank Ivan again for a really nice talk.